three types of heat transfer, let's see, are conduction. And conduction is where you're touching something that's warmer or colder than you are, and it's a molecule-to-molecule transfer. It's very simple kind of heat transfer. It's easily understandable. If you're touching something that's colder than you are, then you're giving heat to it. And if you're touching something that's warmer than you are, then it's giving heat to you. So that's conduction. And that is C-O-N-D-U-C. Okay, and then the second simple form of heat transfer is convection. And that's the way most of us heat our houses. I call it scorched air. Because it's not a very efficient form of heat transfer. I mean, air has like no heat capacity. So the reason that we use scorched air to heat our houses is because it's very controllable. You set a dial, you got a blower, you got ductwork, you turn the dial, you can heat up a house pretty quick. But the problem is that you're not really changing the radiant temperature of the house unless you've had it warmed up for a long time. And that's the third form of heat transfer, is radiation. And radiation is magic. It's line of sight, meaning right now, I know these are not low E windows. I'm looking at that building over there and I'm radiating heat to it. That building is sucking heat from me right now at 186,500 miles per second. It's the speed of light. You know, and it's happening all the time. Anything that you're inside of is either giving heat to you or accepting heat from you. Or if it's exactly the same temperature, then you're neutral. But that's what radiant transfer is, and it's a third power transfer. And I actually failed calculus in college, so I don't really know what that means, but it's super efficient. And think about it this way: if you've ever been around a campfire and it's freezing cold outside, and you're standing around that campfire, the front of you is warm. It's not because the air next to your body is all that warm. It's because the fire is giving heat to you through radiant transfer faster than your body can give heat up to the air. So if you've ever noticed, this is another way it makes it a little clearer. If you've ever noticed when it gets really, really, really cold outside, you have to turn your thermostat up higher. It's not because your furnace isn't kicking out 65-degree air anymore. It's that outside wall is now much colder, and it's sucking heat from you much faster than it was when it was only 40 outside. So you have to bump the temperature of the air up higher to make up for that increased radiant transfer. So radiation, this is one of the reasons that solar works in this climate. Because you can have, and I may draw you the chart for this, but if that wall over there is 80 degrees, you can actually have the air temperature in this room down at 60, and you'll still feel like it's 70. Which is really a bizarre thing to think about, because 60 degrees is not warm, but that wall is radiating heat to you faster than the air can rob it away from you. So that's one of the reasons that passive solar works. And one of the other things that does for you is it makes the indoor air quality better, because mold doesn't grow as well when the air is 60 as it does when it's 70. And the largest indoor air pollutant in Western Washington is mold and mildew. So radiant transfer, where I was going with this, is that if you can keep the air temperature in your house lower, you not only improve the indoor air quality because mold doesn't grow as well, you also reduce your heat loss. Because one of the interesting things about heat loss is the larger the temperature difference between two objects, the faster the heat transfers. So if you look at a graph where you've got temperature difference on one axis and heat loss rate on the other axis, you'd think it would be a nice straight line, but it's not. It goes like this. As the temperature difference between those two objects increases, the heat transfer rate goes up significantly. And that gets into calculus, which I don't understand, but I know it's big. So it reduces the heat loss out of your house when you can keep your indoor air temperature lower. So radiant transfer is cool. Let's talk about thermodynamics a little bit more, and that is spelled T-H-E-R-M-O, dynamics. And there are three laws. I guess good things come in N-A-M. Here we go. I can't always talk and write at the same time. Thermodynamics. There are three laws. First law is energy can't be created or destroyed. Which means, in essence, that all you can do is turn it from one form into another. So the sunlight that comes down to the planet, it stays here, unless it gets radiated out. but it's never really destroyed. And that goes right into number 2, and all energy is from the sun. You know, if it weren't for the sun, we'd be freezing in space. So even oil, you know, indirectly, all the energy on the planet comes from the sun. It's the only energy source we have. Number 2 is entropy is increasing. And entropy is the tendency of things to go from a highly ordered state to a lower ordered state. And this was my reasoning for not wanting to make my bed when I was a kid. It's just going to get messed up again. What's the point? You know. So what it means for us is that everything goes from a higher state to a lower state. Electricity ends up as heat. You know, the lighting in this room is ending up as heat. Everything is ending up as heat eventually. So entropy is increasing, and the third law is heat, because heat is energy, moves from warm to cold. And this seems kind of like a silly thing. It's like, duh. But we think of cold air coming into our house, and really from an energy standpoint, what's happening is heat is going out of the house. And if you ever look at an infrared picture of a house, it's pretty interesting. And it also makes it curious when scientists love computer simulations. You ever notice that? They love to put numbers on things and quantify stuff, and they have real limited applicability for things like solar, because when you do a heat loss calculation on a house, I can throw it out by asking somebody one question. Do you have a cat? Because you know how a cat goes out, right? You open the door and it kind of sniffs and it looks and it backs up and then it sniffs a little. It could take 3 or 4 minutes unless you kick them in the butt. And in that 3 or 4 minutes, with an infrared camera, I've seen this. It's amazing. The cold air is just flying in at the floor and the hot air is just zooming out at the top of the door. And you can get 2 or 3 air changes. Inside air changing with outside air, 2 or 3 in that 3 or 4 minutes. It's amazing. I mean, the average house, an old house in Seattle, will have between 4 and 6 air changes per hour when it's 30 degrees outside. Meaning all the air in your house is changing with outside air 3 or 4 times or 4 to 6 times per hour. And that's huge. I mean, granted, air doesn't have much capacity, so it doesn't take that much energy to warm it up to 65. But still, if it's starting at 30 and you got to warm it up to 65, that's a lot of energy. So that's the number 1 area of heat loss in most houses. Even a new house has between 1 and 2 air changes per hour. That's big. You know, in my old house in Ravenna, I did a blower door test, and this is the only way to check this, is they come out, WSU came out and did it, and they stick this big nylon diaphragm in your doorway. You close all the windows in the house, you cover up the exhaust fans, and this big nylon diaphragm has a monster fan in it. They pressurize your house. So they blow a bunch of air into it until the house is pressurized. Then they cap the fan, and there's a computer that senses how fast the pressure drops. And then they come back and they say, you've got the equivalent of a 1 square foot hole in your house. And then they repressurize the house and they walk around with a smoke wand. And they watch where the smoke disappears. And that's how you know where you've got air leaks. Around windows and doors are the 2 biggest areas. I got my house down to 0.89 air changes per hour for a 1946 house. Now they did the test 3 times because they couldn't believe it. They said, you know, there's no way you got a house this old down to 0.89. I said, I did. I painted it myself. And that's what it takes, is you want to dig out all the caulk. Any place where there's a hole in the siding, you want to dig out all the caulk. Any gap that's bigger than 1/4 of an inch, you don't use caulk. You shove backer rod in there. It's like a foam rope, and you jam it into the crack, and then you put a thin layer of caulk over it. Because the foam will stay flexible. The caulk, if it's more than 1/4 of an inch, it'll dry up and it'll recede, and then you'll have little cracks instead of big cracks. But the foam will stay flexible forever. You just cover it with caulk because the caulk stands up to ultraviolet better. Ultraviolet degradation is the only thing that really deteriorates our house. You know, same with roofing. The rain will knock those little rocks loose and they end up in your gutter, and the rocks are what is protecting the substrate, the fiberglass or the cellulose, whatever is the material underneath the rocks. That's what's keeping your roof from leaking. As soon as those rocks are gone, then the sun is hitting that substrate and it deteriorates, and then your roof wears out. So ultraviolet is incredibly destructive, especially to petrochemicals. You never want to put any kind of foam. Same with plastic glazing, and I didn't bring my plastic glazing. But if you're going to use plastic glazing, make sure it's UV stabilized. For replacement windows, what I'm also going to do in the new house, since I don't have wood frames, I've got single pane metal windows, I'm going to go with Anderson Renewal. It's a fiberglass and wood frame, and it's a very cool system. I don't like vinyl. I mean, vinyl is energy efficient, but it's horrible stuff when they produce it. It makes dioxins and PCBs and all these bioaccumulating toxins, and it's just nasty. Yeah, and it's not dimensionally very stable. You know, it turns chalky and it changes dimension too much, and you know, it's cheap. The Renewal is probably 25–30% more expensive than the vinyl is, and then the wood is about twice the cost of vinyl. So this is what we're supposed to be talking about, energy efficiency. So we got the thermodynamics, heat transfer vocabulary. BTU is how we measure heat transfer. BTU stands for British Thermal Unit, and it's the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit. And that's the way we look at capacities of heating systems and therm. If people have gas heat, this is what they will show you on your bill. 1 therm is equivalent to about 100,000 BTUs. And that's also equivalent to 1 CCF, which is 100 cubic feet of gas. So I think they just do this to confuse us, so we can't really compare gas to oil to electricity. 1 gallon of oil, and this is something that I like to point out. When I did all this stuff to my house, I thought about changing out the furnace, and I actually could have got a little bit of help from the city to change the furnace, but I had an old oil furnace. It was from the 1950s. It was a Sears Home Mart furnace. And the thing, it was just a tank. It had been working just fine. It was running at about 80% efficiency, which is not bad for an oil furnace. And so I talked Laurelhurst Oil Company, which is about a mile away from here, into carrying biodiesel. And I was running my furnace on 60% biodiesel. Biodiesel reduces the particulates by about 70%. It reduces the the sulfur dioxide and the nitrous oxide by about 80%. You get about a 5% decrease in actual heat capacity by using biodiesel, but it's locally produced. I mean, we're getting the feedstock from Iowa. It's being produced down in South Seattle now, about 1 million gallons a year. And if you're really cool, you can produce it yourself. It takes about a 10 by 10 space in your garage. It takes about 10 hours a week, and you'll be producing 100 gallons of biodiesel. You can run your car on it. You can run your furnace on it. I suppose you could run a generator on it. And it's like barely flammable. So it's not a toxic chemical. The fire department, technically, they might have a problem with you doing it in your garage, but there are so many people doing it. And there is an argument there that the stuff is barely flammable. It's not like producing gasoline in your garage. That is assuming 70% efficiency. Yeah. So that's probably a little higher efficiency. All right, now let's talk about electricity. So most of us deal with kilowatt hours, and this equals 1,000 watts for 1 hour. And that's 1 kilowatt hour. So if you ever want to know how much electricity you're using, you can look on your bill. You can also look at your appliances, like for people that want to be off-grid. Best thing to do is take a sizing chart and go to every appliance that you're going to be using and look on the back and see how many watts that appliance is drawing, and then try and calculate how many hours a day you're going to be using it, and then you'll come up with watt hours. Kilowatt, okay, and 1,000 watts, okay, we'll do this. kW equals 1,000 watts, and that equals 3,413 BTUs. And this is at 100% efficiency, because it's no trick to turn electricity into heat. We can do it 100% efficiency all day long. It's not hard. It's like saying that, a Cadillac's going to burn all the gas you put into it. It will. And you'll get 3,413 BTUs out of your electric furnace. If you go with a heat pump, Heat pumps are really nice. What heat pumps do, in a nutshell, is it's sort of like a backwards refrigerator. It's taking a material that boils at a very low temperature, and it's sending this material out into a coil outside, and it's releasing the pressure on it, because when you put something under pressure, it takes a lot more energy to make it boil. When you reduce the pressure on it, then you can boil it much more easily. So they take this Freon, they run it out into this big evaporator coil outside your house, and they've got a huge fan, and they blow air over the coil, and you're boiling Freon. Then you're taking all this Freon that's picked up some heat from outside, and it'll pick up heat even at freezing outside, because stuff boils at like -40. Freon is an amazing material. And they bring it back into the house. They got a big volume. They take that volume and they run it down into a small volume. And when you take a big volume and pressurize it into a small volume, you've increased the heat. All those molecules that are bouncing around, now they've only got this much space to bounce around in. So it increases the temperature of the Freon. You run the Freon through a radiator and blow air over it, and that's basically how a heat pump works. That's an air source heat pump. A ground source heat pump has a coil, and instead of running air over that Freon outside, they're actually taking water. Like you can dump these pipes into a pond, or you can bury them in your backyard. And an air source heat pump has a coefficient of performance. So air heat pump, which is mostly what you'll see around here, 2-to-1. So for every unit of electricity that you put in, you're getting 2 units of heat back out. So it's like getting free energy. It really is. The other one is called a ground source. And they're getting about 3-to-1. The problem with heat pumps is that, number one, it's an expensive system. This system here is about $10,000. This system here starts at about $20,000. And for a climate that has a very mild heating season, that's a lot of money to pay for a super efficient system. You know, I like efficiency, but if somebody has a limited budget, putting $20,000 into a ground source heat pump, it just doesn't make sense. And the good thing about these is on the east side of the mountains, you can run them backwards, and they will do air conditioning in the summertime. So if somebody really needs air conditioning, heat pumps are the way to go. They're much more efficient than, you know, a little room air conditioner or even a central air conditioner. But on this side of the mountains, it just doesn't pencil out. At 5-6 cents a kilowatt hour, you know, I'm not sure the house will ever realize that many savings. And in general, I recommend higher than code insulation levels, because insulation's cheap. And even if you live there for 7 to 10 years and you're not getting the benefit of all that insulation, over the life of the house, it will certainly pay for itself many times. So I think it's worth doing. Builders that say their houses meet energy code, you know, and they brag about it. I've actually heard builders do that. Oh yeah, we got R30 in the ceiling, R19 in the floors, and R19 in the walls. They should just say if the house was any worse, it would be illegal. Because it's, you know, that's a starting point. It's not the best you can do. And that dumps us right into R value. Okay, so we talked about kilowatts. A megawatt is just a million watts. Sorry. So let's talk about heat, since that's where passive is about. So insulation, we all know what insulation is, and that is measured in R value. R value is resistance to heat flow, and it is, for the engineers in the audience, measured in BTUs per square foot per degree Fahrenheit of temperature change per hour. So the higher the R value, the better insulation you've got. And code is a starting point. U value, so this is the way we measure walls, ceiling, and floor. You always look at R value. U value equals 1 over the R value. It's just the inverse. And I don't know why they do it that way, but just to confuse us, I suppose. Gotcha. And they use this for windows and doors. So the lower the U value, the better insulator you've got. And if you want to know what code is, walls are 19, ceilings are 30, to 38, depending on whether it's a vaulted ceiling or not. Floor is also 19 now. And then perimeter, well, we'll say concrete is 10, concrete floor. And then doors and windows, I think windows, it ranges. There's a range that you can use for windows depending on how much glass you have and how much solar you've got. There's actually some exemptions from the window requirements based on solar, which is really not all that relevant now because what they used to say is if you had 25% of your floor space in glass, your windows had to have a U value of like 0.6 or 0.4, I think it was, for 25%. Finally, they just said you can have unlimited glazing. You can build a glass box in Washington State now, and you will meet energy code if your windows have a U value of 0.33. Okay, we got U value. Infiltration. Infiltration is air leaks. Typical new house has 1 to 2 air changes per hour, meaning outside air is changing with inside air 1 to 2 times every hour. That's air changes per hour. Typical new. Typical old is 4 to 6. So that's huge. Now this is the #1 area of heat loss, is air leaks. In pretty much any house, it's big. This dwarfs every other kind of heat loss. #2 is windows and doors, because you can see, window is, a really good window is 0.33, a door is 0.20, but still, that's really small compared to these numbers. Also, those window and door U values, that's the center of the glass, which is the most efficient part of that window. Where the spacer is, where the edge of the window is, that's the worst part. The frame is not all that good usually. All right, so infiltration, air leaks, stratification. When I was working up in Granite Falls, I was in a building that I didn't think was possible. Stratification is temperature difference between ceiling and the floor. Ceiling to floor. And in this building, it had a high ceiling, sort of like this. The difference between your head and your feet was 20 degrees. Gospel truth. I mean, there was water down in the crawl space, so that floor was sucking energy from you. This is Granite Falls, so it's cold up there. The water under the floor was barely not frozen ice, so it was probably, the floor was sucking energy from me. I would guess that floor surface temperature was probably about 36 degrees maybe. And they had gas heaters going full time, all the time. And so up at the top of your head was probably 70, 75 degrees. And we had a bunch of older people in the room and they were cold. And so anyway, stratification can be huge. That's one of the disadvantages of having tall ceilings. If you're going to have a really high ceiling, put a ceiling fan. That'll help. In the wintertime, it'll stop the heat from all ending up way up there where you're not. And in the summertime, it'll keep the air moving, which makes you feel cooler because it increases the evaporation off your skin. Infiltration. Actually, they're all good questions. But, less than or equal to 0.35 required HRV. Or fresh air. And I just say HRV. HRV is a heat recovery ventilator because the EPA has said when you get down to 0.35, it's unhealthy. You got to bring in fresh air. So you can either do it through your scorched air heating system because most heating systems now require that you bring in fresh air. You can also do it through a heat recovery ventilator, like if you've got a hydronic slab, then you don't have ductwork going all over the house. And so this HRV, what it does is it takes the warm, moist air that's going out of your kitchen, bath, and utility room, and you're required to have exhaust fans in those 3 rooms by code. They've got to be 50 CFM in the bath and utility room and 100 CFM minimum in the kitchen. And so for every cubic foot of warm, moist air that's going out, it goes through a heat exchanger. So you've got the warm, moist air going out, and then there's a radiator here. And then the air coming in passes through this radiator too. This is giving its heat up to the radiator, and that radiator is giving the heat back to the air that's replacing it. So they claim that you can save about 60% of the energy that would be going out your exhaust fan by using a heat recovery ventilator, which is pretty big. There's another system, and they just changed the name of it. Used to be called the GFX. This is another very cool energy efficient thing. It's not required, but it's your main sewer stack. So this is going out to the street. And this is, use Mike Rowe, we'll say poo. There's poo going down here. But there's also water. And what this thing is copper pipe. So there's water from this, let's see. Let me get this right. All right. So you're up here taking a shower. All the water going down this pipe, it actually goes down the sides of the pipe, so we'll forget this. That's not what we're doing here. All right. The water, when it goes down a pipe, there's a main 4-inch cast iron pipe down in your basement, and that's where all the sewage goes down before it goes out to the street. It actually doesn't go down the center of the pipe. It goes around the outside of the pipe. And so what they do is they replace either a 3-foot piece of pipe or a 6-foot piece of pipe down in your basement with this piece of copper that has other copper wound around. And this is your water heater. And what happens is as this warm water is going down the drain from your shower, it's giving up its heat to the water in this copper coil. And the water in this copper coil goes back to the water heater. So instead of pulling 50-degree water off the street, you're pulling water that has already picked up a bunch of heat off of this coil, and that's what's feeding the hot water tank. And then the hot water tank gives the water back to the shower. So it's really good for showers. It's not great for things like washing machines and dishwashers where you've got a big dump of water down the drain and then it takes a while to fill back up. But for showers, this thing it'll pay for itself quick. And I think it's called a heat recovery pipe or something like that. It used to be called GFX. I'll bet you if you go to gfx.com, there'll probably be something to take you to the new site. Or you can also go to Green Depot. Green Depot is the company that sells these. They don't manufacture them. Or you can go to the Eco Building Guild, the Green Pages, and they're certainly in there. Green Pages is like a directory of all the different folks involved in the guild. Suggested readings. I didn't bring any of these books with me, but the Passive Solar Energy book is out of print, but you can still find it in used bookstores. They printed thousands and thousands and thousands of them, so you can still find it. You can find it on Amazon. That is probably the best book for passive solar. And the only things in the book, the copyright is 1984, but the only things that have really changed are insulation values and how good the glass is. The solar resource is still exactly the same. The mass storage materials are pretty much the same. The new Solar Home book is one that is still in print. That's by Bruce Anderson. That's a good book. Passive Solar House by James Cacciadorian. That's a really cool one for seasonal storage. Because in this climate, if you really want to do more than about 50% of your space heat with the sun, you're going to have to get pretty elaborate. You can do it but it's going to require a sunroom, and that sunroom should be isolated from the living space because on middle of December when it's cloudy and it's cold outside, you want to just shut it off from the house so you're not sucking heat from the house to try and keep the sunroom warm. But on nice sunny days, then you open up the doors and you've got good gain. The James Cacciadorian book, The Passive Solar House, he talks about doing what he calls an air core slab. And it's a slab-on-grade foundation, and he takes concrete blocks and turns them sideways. So these are the blocks that have the voids in the center. They're like cinder blocks. You lay them on their side, you're taking solar energy and you're pushing it through this floor, and so you've got all this surface area that's soaking up heat. Then you've got a concrete slab on top that gives the heat up to the living space. It's a very slick system. I've done 2 of these now over in eastern Washington. I haven't done one on this side of the mountains because it still makes me a little nervous, because in the wintertime, 67% humidity is the average, and if you're pushing moist air through this concrete block, it's going to condense out somewhere, and if you get a bunch of moisture down in there and it starts growing mold, you're screwed. There's going to be no way to access it or get rid of that mold. So it's the same reservation I have about rock bins on this side of the mountains. I know that people have done them in the past, but if you don't keep that air going through there fairly dry, you can have stuff growing in them. once it starts growing, it's almost impossible to get rid of it. So I'm more about daily storage rather than seasonal storage, maybe a couple days worth of storage, but seasonal storage on this side of the mountains, I'm not sold on it. It seems like the potential problems far outweigh the benefits. You know, the difference between 40 or 50% solar savings to 60 or 70% solar savings just